Hello everyone, welcome back. So today we will look at binomial distribution. So we will start off with what is binomial distribution. We will look at the equation and we will also understand it better with some examples. And then we will also try to plot the probability mass function. And we will also look at Python code. So how you can find the binomial probabilities if you have a real scenario. So this is all we are going to discuss in this video. So let's start off with the definition of binomial distribution. So the binomial distribution with parameters n and p is the discrete probability distribution of the number of successes in a sequence of n independent experiments, each asking yes no questions and with its own boolean valued outcomes, success or failure. Now let's look at the equation of binomial distribution. So if you want to know the number of successes, that can be k. It can be calculated using n choose k. So this is how we write n choose k. There is another representation which is nck. So you can also write nck as n choose k. And this is equal to n factorial divided by k factorial n minus k whole factorial. So that's what n choose k means. And here p is the probability of success to the power k, and 1 minus p is the probability of failure, which will be to the power n minus k. And k can range from 0 to n, and x represents the number of success in n independent trials. And here we will have mean equals to np, and our variance will be np 1 minus p. Now let's take an example and understand this better. So let's say we have a random variable x where this is number of times we get tails when we flip it for 4 times. So the first thing first, we need to find total number of possible outcomes. So we have 4 slots, 4 coins. Each will have 2 possible outcomes, head or tail. Same for these two, same for this one, same for this. So we can say that this will have 2 possible outcomes, 2 possible outcomes, 2 possible outcomes, and 2 possible outcomes. So this will be nothing but 2 to the power 4, which is nothing but 16. So this is what we have here. Now we want to see number of times we get tails when flipping a coin for 4 times, right? So we have possible outcomes is x can be 0, x can be 1, 2, 3 and 4. So there can be 0 tails, there can be 1 tail, there can be 2 tails, there can be 3 tails. There's also a chance that all the times it will get tails. So that's what we have right now. So if we try to find x equals to 0, so in how many scenarios we will have 0 tails? So there will be only one possible case where we will get all the heads, so basically just one. So this will be 1 by 16. Now let's try to use the formula which we saw earlier, which was n choose k. So how we can find this 1? So we want to find 4 choose 0. So we want to see 0 tails in 4 trials. So we know the formula, which is 4 factorial divided by 0 factorial, 4 minus 0 whole factorial. This is nothing but 4 factorial divided by 4 factorial. This is equals to 1. So you can see we are getting 1 here as well. Now we want to find x equal to 1. So now how many total possible scenarios are there where we will have one tail? So it can come in the first place and all the others will be head. It can come in the second case and all the other will be heads. So like this, we have tossed it 4 times, so we will have 4 possible cases. So we can say 4 by 16. Now again we will try to use the formula and see if we get 4 again. So we will have 4 choose 1. We will have 4 factorial divide by 1 factorial, 4 minus 1 whole factorial. So this will be 4 factorial divide by 3 factorial. So we know this is 4, 3, 2, 1. This is 3, 2, 1. This will cancel out this and we are left with 4. Now we will try to find x equals to 2. Now that I have proved the point that we can use this particular formula to calculate this numerator, I'm gonna directly use the formula. So we have 4c2 4 factorial divided by 2 factorial, 4 minus 2 whole factorial, 4 factorial divided by 2 factorial into 2 factorial. So this is nothing but 4, 3, 2, 1, 2 into 1, 2 into 1. So 2, 2, this is nothing but 4. We will cancel out this and we will be left with 6. So now we can write it as 6 by 16. Now we will have x equals to 3. This will be 4c3. You can either pause the video and you can calculate other as well, and you can also match if you are getting it correct or not, but I will calculate it here for you so that you can match your values. 3 factorial, so 4 minus 3 whole factorial. So now we will have 4 factorial divided by 3 factorial, which is same as this one, 4. So this will be 4 by 16. So now you can see it is showing some sort of symmetry. Now we will find last, which is x equals to 4, 4c4, which is 4 factorial divided by 4 minus 4 factorial. This is nothing but 4 factorial divided by 4 factorial, which is nothing but 1. So you see the symmetry, 1, 4, 6, 4, 1. So this will be 1 divided by 16. Now let me draw a histogram for you to show you how the probability mass function looks like. So the maximum value that we had was 6 by 16. So if we take middle value around here, this will be 3 by 16. So we can say that this is 4 and this is 5. And we can say this is to be 2, 1 and 0. And possible outcomes we had were x equal to 0, x equal to 1, x equal to 2, x equal to 3, x equal to 4. For x equal to 0, we had 1 by 16. For x equal to 1, we had 4 by 16. For x equal to 2, we had 6 by 16. For 3, we had 4 by 16, and for 4 again we had 1 by 16. So I will complete this as well. Yeah. So you see this looks very much like normal distribution because it is forming some sort of bell curve here. So normal distribution is for continuous variables, and binomial distribution is for discrete variables. So if you, here we have seen only 4 trials or 5 trials of 5 possible cases. If you see more number of trials, so let's say you flipped a coin for 10,000 times, you will see these bars will be even smaller. So in that case, it will start to look like a continuous variable, and it will look more like normal distribution curve or bell-shaped curve. But in normal distribution, you can always have values between these discrete values. So in normal distribution, you can have 0 0.01, 0 0.02, even 0.5, something like that. But here you will always have 0, 1, 2, 3, or whatever the step size is defined. So yeah, this is the probability mass function, and for normal distribution, when we have bell-shaped curve, that will be probability density function. Now let's take a real case scenario where you are working as a data analyst for a product company, and your company is doing a market research on a new product. They conducted a survey, and after your data analysis, you found the following. So after data analysis, you found 20% of the existing customers are willing to buy the new product. So that's what you found. Now your manager wants to know what is the probability that at least 25 out of 100 customers will buy. So first we will try to answer this question, and after that we will see what will be the probability for exactly 25 out of 100 customers will buy. So for first one, what we can do is to find the probability of at least 25 out of 100 customers will buy the product. We need to calculate the probability of 25 or more customers buying the product. This can be done by adding up the probabilities of all possible outcomes where 25 or more customers buy the product. So this can be written as this equation. Now the thing is, it can be very tedious because you saw the formula, and if we just try to find one probability for x equals to 25, it is going to take time. So in real case scenario, we never will find these probabilities by hand. So the answer for this question will be 0.131, which I will show you in the notebook section, where I have found this value and how you can find this particular value using SciPy package. And we will actually try to find the value for exactly 25. So for that, it's just x equals to 25. So here we will put the values that we have. So the probability for success is 0.2 because 20% of the customers are willing to buy. So that is what we have. That will have power of 25, and we will do 1 minus 0.2 to the power 75, which is nothing but 100 minus 25. So this will be 100. Choose 25. 0.2 to the power 25, 0.8 to the power 75. So this will be equal to 0.044. Again, this value also I calculated using SciPy package. So I will show you that now how you can do that. So now let's move on to the notebook. So this is the first question. If 20% of the customers are willing to buy a product, what is the probability that at least 25 out of 100 customers will make the order, right? So here you can see this particular code. I'm using scipy.stats. From that I'm using binom, and n is equal to 100 because that's what the total number of trials we are doing, or total number of customers we have, and the success probability is 0.2, and out of 100 we want to find at least 25. So that is what k is, and the probability is calculated as 1 minus binomial dot cdf of k minus 1, and here you will pass n equal to 100 and p equal to 0.2. Now you might ask why 1 minus, right? So we calculated probability for 25, 26, 27 up to 100, right? So if we calculate those many terms, it will take too much time. So what we can do is we can always calculate for 0 to 24, and we will subtract it from 1, and that will give us the probability for 25 or greater. So that's what I have done there, and here you can see the probability is 0.131, which I showed you in slides as well. Now for the second question, here you have, if 20% of the customers are willing to buy a product, what is the probability that exactly 25 out of 100 customers will make the order? Now again, all the same values, but here you will see that I have just passed k, n and p, and we have got the value as 0.043. So that's how you can actually find the probabilities of any distribution, actually not just for binomial distribution. So you can always use, instead of binomial, you can use normal distribution. As for your task, what I would suggest you is generate binomial random variable and plot its probability mass function, and you can do this using numpy.random.binomial. So you can generate random binomially distributed data using numpy.random.binomial, and try to vary the number of samples. So try to generate very small number of samples, somewhere around 10-15, and then go all the way up to 10,000, maybe 100k as well. So after doing that, you will see that it looks very much like a normal distribution. So that's what your task is. So this is it for this video. Hope to see you in the next one. If you have any doubt, query, you can always post it in the comment section. I'll be more than happy to clarify that.